So in this particular lecture, what we will talk about is more on the pass transistors and then the transmission gates, right? So I've drawn a pass transistor here. In this particular case, it is a pass transistor, means a single transistor, and I've considered the NMOS as the pass transistor here. And then we need to understand the working of this particular NMOS transistors. The pass transistors can also be designed using the PMOS transistors, and that is something we will see in the future slides. So let's begin with this, with the NMOS transistor. So I've drawn the NMOS transistor here. The input is provided with a VDD power supply here. So the VDD is this particular, VDD. The drain and source are there, and let's say that for the drain, the VDD is being applied. So a power supply is there. I have switched on the power supply, and that's why earlier if it was wired, this particular terminal of the transistor was directly connected to the power supply, and then if it was switched, so that's why you will see a kind of a step input, right? 0 to VDD. So I've switched on the power supply, and this particular terminal receives a power supply of VDD. And let's say that on the other side of the terminal, we have arranged a capacitor. So a load capacitor is there. So this is nothing but a load capacitance is being added. Right? Even if there is no load capacitance, the source and then the body, or rather, whatever the source or the drain, with respect to the body, so the terminal with respect to the body will always have the junction capacitance. Right? So irrespective of the load capacitance, there will always be a junction or a depletion capacitance or a parasitic capacitance, which we had seen in the previous lectures. Right? So I have drawn this particular capacitance, and on this particular terminal we have switched on the power supply. This is anyways there. This VDD is applied to the gate. Okay. So because it's an NMOS transistor, we know the gate terminal here. This is the gate terminal G. We don't know which terminal is this, whether it's a drain or source, although I've written it as DNS. Let's try to validate whether it is actually drain. Right, so to begin with, the capacitor is not charged at all. So the capacitor carries a voltage of 0. So it has a voltage of 0 here. On the other side of the terminal, it has a potential of VDD. So for an NMOS, the drain should be at a higher potential than the source, and that's why we have this side covered as drain, and then this side covered or called as source, right? So if now I have this particular terminals now, and then the power supply is also labeled in this particular transistors, so we should be able to state which operating region the transistor is operating, right? Whether it's a linear cutoff or saturation region. So if I have this particular VGS value, which is nothing but VDD, minus 0, because initially it says 0 volts. So initially, right, VGS is VDD, VDS is VDD. So initially, the transistor will be in the saturation region. Is that correct? So the VGS value is VDD. The VDS value is also VDD because initially it is 0 volts. So initially the current will be flowing from VDD, and it will be charging the capacitor. So the charging capacitor or the charging current for the capacitor is the saturation current. So I'm going to say that this is nothing but I saturation. All right. This particular source potential, while the capacitor keeps on charging, it is going to have an increase in the voltage. So across this particular node, it is going to have an exponential profile. So the capacitor charges, right, and then it should have an exponential profile of the voltage for the capacitor with respect to the time. So the capacitor charges, and let's say that after some time it will reach to a 0.1 volts. VDS value is still VDD minus 0.1. VGS value is still VDD minus 0.1. So it will still be in the saturation region. Okay, so it continues to charge the capacitor via the saturation current. Okay, and it will reach to a value of VDD minus VT. So the capacitor charges till VDD minus VT. After that, once the source potential reaches VDD minus VT, VGS turns out to be less than VT. So once it goes beyond VDD minus VT, so let's say that VDD is 1 volts, VT is 0.3 volts. So until 0.7 volts, it is charging the capacitor. So this particular configuration is charging the capacitor. But once it goes beyond 0.7, let's say 0.71, VGS turns out to be less than 0.3. So there is no channel that is formed here. So the channel is not there for the current to drive from the drain to source and then charge the capacitance. So the capacitance can charge till VDD minus VT. So if I have a VDD here, it can charge till VDD minus VT. So the charge to VDD minus VT till the channel is formed. What it implies is, if I have a pass transistor and if I want to supply the logic from one end and then see the other end voltage, if I pass a logic 1 here, so a logic 1 on one terminal, which is nothing but VDD, on the other side, I will get VDD minus VT, VDD minus VT. It is called as a poor logic 1. Poor logic 1 because it is actually closer to VDD. VDD minus VT is actually closer to VDD, far away from 0, logic 0, and that's why it is called as, it is passing logic 1, but it is passing a degraded logic 1 or a poorer logic 1. Okay. So this is about, passing the logic 1. So NMOS transistor passes a degraded logic 1. Now let's see what happens if I want to pass a logic 0. So passing a logic 0 means this particular power supply which is there, which I had switched on in this particular case, I'm going to switch it off so that it connects to the ground. So there is a 0 volts here. So this particular terminal, I'm going to connect it to the ground. Whereas this capacitor is now completely charged to VDD minus VT. That's the maximum it can go. And we will see that whether this particular capacitor discharges to 0 volts. Because on the other terminal, it is now connected to the ground. So the capacitor now starts discharging, right? It starts discharging using the channel here. The channel becomes the path for the current to flow from one terminal to the another terminal of the NMOS transistor. Now we have to label this. So the label in the sense, the gate, source and drain, which of these terminals are the drain and the source terminal. The gate is very easy to identify. It is gate, and this particular terminal is the gate terminal, and we know that it is connected to the VDD. We don't know which one is the source or the drain here, right? So if this particular terminal is VDD minus VT. This particular terminal is connected to the ground, which is nothing but 0 volts. So whichever terminal has a higher potential, we will call it as the drain terminal. So similarly, in this particular case, the first case, we also labeled or defined the drain terminal for the terminal whichever one is higher. So the potential, whichever potential is higher, VDD or 0, we will call it as the drain terminal, right? So this drain terminal is nothing but VDD minus VT because it is greater than the 0 potential. So this becomes the drain and then this becomes the source. So in this case, if VGS is there, VGS will always be VDD minus 0 because this is anyways grounded. So VGS will always be 0. Here in this case, VGS was changing continuously as the capacitor was charging. So VGS was, starting value of the VGS was VDD, and then as the capacitor voltage increased, the VGS value started decreasing and until it reached VDD minus VT. Beyond that, the VGS value turned out to be less than VT, and thereby the channel was disconnected. Here the VGS value is always VDD minus 0, so it is greater than VT value. So there will always be a channel here in this particular transistor. Thereby the capacitor can always have a path. It ensures that there is always a path for the discharging. So it starts from VDD minus VT and then discharges completely to 0. So that's what I've written here, discharge to 0, and it is also passes the logic 0 successfully. So it doesn't stop in between. It doesn't stop in the middle. It reaches to the 0 volts, right? And that's why if I apply on this particular terminal a 0 voltage, it passes the 0 successfully. Whereas for an NMOS transistor, it passes a degraded logic 1 because it is limited till VDD minus VD. Okay. Going forward, let's take a look at the PMOS transistor as a pass transistor again. So if I look into this, so the PMOS transistor again the same thing, the gate is connected to the 0 volts because I want the gate to be at a negative potential than that of the source. So VGS value turns out to be negative for the PMOS. So I'm putting it 0 on both the cases. 0 volts of the gate represents, if I here it is a gate. So 0 volts of the gate represents that the PMOS transistor has a gate potential of 0. And the other two terminals, so again, if I have connected a power supply and switch on the power supply, so I'll get a step response, VDD. So I'm having a VDD potential connected to the one terminal. So for a PMOS transistor, we know that the terminal which has a higher potential, that should be the source. In an NMOS, drain should have a higher potential than that of the source, whereas in a PMOS, the source should have a higher potential than that of the drain. So whichever one has a higher potential, that will be the source. So in this case, the power supply is connected to the terminal, and that's why we call it as the source. Because on the other side, even if the physical capacitance is connected, right, the capacitor initially will be at 0 volts. So this particular terminal potential will be less than that of the other terminal potential. So this will be considered as source, and the other one is considered as drain. VGS value for this PMOS transistor. VGS value for this PMOS transistor is nothing but always minus VDD. Always. Right? Because the other terminal, we have the capacitor connected and the capacitor is charging. It doesn't disturb the VGS value. So the VGS value is always minus VDD, which is much less than that of minus of VT or minus of 0.3 volts. Thereby, the PMOS transistor has a path constantly available for it to charge the capacitor. So the capacitor, even if it starts from 0 volts, it will actually charge till VDD. So for the PMOS pass transistor, so it charges to VDD and it passes the logic 1 successfully. Okay. On the other side, if I have it grounded, so if the power supply is now switched off, so I will have this particular terminal connected to the ground. So this particular terminal connected to the ground. And the other terminal, we have now, let's say that the capacitor is charged to VDD. So whichever terminal of this particular PMOS transistor has a higher potential, that particular terminal will be labeled as source. The other terminal will be labeled as drain. Right. So this will be the source and then this will be the drain. So this is VDD. And let's say that this particular capacitor starts with VDD. So this will be the source and then the other one which is connected to the ground will be the drain. VGS value as the capacitor discharges, that means that the potential across the capacitor is going to decrease. Initially, it starts from VGS value as minus of VDD, But as the capacitor discharges, this VGS value is going to decrease. In fact, it is going to become closer and closer. It was more negative, minus VDD, and it's coming closer and closer to the 0 volts, right? So it starts discharging and it discharges till it hits the VT value. So the moment VGS becomes minus of VT, beyond that, the channel which is formed here, right, the channel that is formed in the PMOS transistor will not exist anymore, right? So it will discharge till VT. So the discharging of this particular PMOS transistor is held or it's limited to VT till the channel is formed. Beyond that, the channel doesn't exist, so there is no discharging path. So the PMOS transistor, it passes a degraded logic 0, whereas the NMOS transistor passes successful logic 0. The PMOS transistor passes the successful logic 1, whereas the NMOS transistor passes an incomplete or a degraded logic 1. So hope this is clear. So I've drawn two different configurations here. One where we have a stacked transistors the output of this particular first transistor, the output of the first transistor is connected as a gate to the next transistor. The next transistor output is connected to the third transistor, and the output of the third transistor, it is connected like that. So in this particular configurations, I have 3 transistors, and then we have the supply of VDD. So what should be the output of the third transistor? So if this is VDD and then the gate is VDD, right, and it is an NMOS transistor, so it is an NMOS configuration here. So we know that the output will be charging till it reaches VDD minus VT. Beyond that, this channel or this transistor will go into the cutoff. So it will go till VDD minus VT. So if this is VDD minus VT and this is VDD, so it is going to charge this particular node. It's going to charge till VDD minus VT minus of VT. So it is going to charge till VDD minus 2VT. Right. Similarly, for the third transistor, it will go till VDD minus 3VT. For the N transistors, it will be nothing but VDD minus NVT, provided it doesn't go below that of the VT value. Right. So this will be the VDD minus NVT as a general expression. Right. So if I consider VDD to be 1 volts and then VT to be 0.3, right, so it will be 1 minus of 3 into 0.3, so it will be 0.1 volts, which is not true, right? So because this one will have 0.4 volts, right? And so to begin with, this one will start from 0 to 0.1, so it will start from 0 to 0.1, and so it will reach till 0.1. So sorry, so this will be VDD minus 3VT. That is correct, right? So, and then if I have the fourth transistor, so this will be 0.1 volts, which is very, very less than that of the VT. So the fourth transistor will always be in the cutoff region, right? So if there is a capacitor, there is no path connecting in the fourth transistor, so that particular channel doesn't exist for the fourth transistor. So the output of the fourth transistor will always be the 0 volts. Okay, and then the fifth transistor will also be in 0 volts. Okay, hope this is clear. Second configuration where we have again a cascaded one. So that one I call it as a stacked one, and then this one is called as a cascaded one. The reason is nothing but the output is connected to the input of the pass transistor, and again the output of the second transistor is connected as an input to the third transistor, and so on. And finally, so after 4 transistors, cascaded 4 transistors configuration, what should be the output here? So if I am supplying VDD here and the gate of all the transistors in the cascaded configuration is VDD, what should be the output here? The output is nothing but it will reach till VDD minus VT, beyond which it cannot go because this particular transistor will be in cutoff. So it will drive till VDD minus VT. The next transistor, again it will drive till, so it is going to pass this particular transistor to charge the capacitor at this particular node, right? So this is the current. But the charging, the voltage profile of this particular charging, it will reach till VDD minus VT. The reason is beyond that, the VGS value of this second transistor will be less than VT, and then the channel here will be broken. So thereby it will charge till VDD minus VT. Right? Note that this VDD minus VT, it has nothing to do with this particular voltage. It has nothing to do with this particular voltage. Right? It has nothing to do with this particular voltage. This delimiting factor is nothing but coming from the gate voltage. Whatever is the gate supplied voltage, it is actually derived from the gate supplied voltage. Again, this VDD minus VT is actually derived from this particular gate voltage, and then this VDD minus VT is also derived from this particular gate voltage of VDD, so beyond which the transistor will be in cutoff. Therefore, the output voltage, the maximum output voltage will be VDD minus VT here. In fact, if I keep on going for the N transistors, right, the output of the nth transistor will also be VDD minus VT. right? Hope this is clear. Moving ahead. Now let's take a look at the transmission gates. All right, so earlier we had seen the series, the inverter, right, which is nothing but a series of the PMOS and NMOS transistors. So here, instead of having a series of PMOS and NMOS transistors, what we have is a parallel combination of PMOS and NMOS transistors. Right, so I have a PMOS transistor, this one, the bubbled gate shows that that is a PMOS transistor, and the unbubbled gate is an NMOS transistor. Okay, so the gate of both these transistors is very, very clear. So I'm going to write this gate as G and then this gate as G. On one side, the gate is supplied with the VDD. On another side, the gate is supplied by 0 volts. So the moment the gate is supplied by VDD or the gate is supplied by 0 volts on the PMOS side, we know that this transmission gate should drive some current, right? Unless the VGS value turns out to be less than VT, right? On either side, VGS value is less than VT for NMOS, and VGS value is less negative than that of minus of 0.3, then we can say that it is in cutoff region. Okay, so we have connected the two terminals, the two diffusion nodes here, and then we have also connected the diffusion nodes of the NMOS and PMOS transistor. So basically we have tied both the diffusions and then fed it into a power supply here. Right, again it's a step response. The reason is I have switched on the power supply. So I'll get from 0 volts. Now at this particular instance, it is switched on. So I will get the VDD power supply. So the moment it is the VDD power supply, right? The moment it is the VDD power supply, and I need to have the labelings of the terminals so that I can find out or I can estimate the current, and then I can estimate the charging profile of the capacitor. So on the other side, there is a capacitor here. It could be the load capacitor connected to the ground, right? So if this is VDD for an NMOS transistor, whichever one, earlier this capacitor, formally this capacitor, load capacitor is connected at this particular terminal. The load capacitance, initially it is completely discharged. So the potential here is 0 volts. So on the other side of the terminal, it is the VDD. So whichever terminal has a higher potential, that should be the drain. The other one should be nothing but the source for the NMOS transistor. For the PMOS transistor, it is the opposite. So whichever terminal has a higher potential than the other one, that should be called as a source, and the other one should be called as a drain. So now I have this particular configuration of NMOS and PMOS where the same tied node is having a different terminals. So the NMOS has a drain here, whereas this particular tied node has the source represented for the PMOS. And similarly on the opposite side, NMOS has the source here and then the PMOS has a drain here. That's perfectly fine. Right, so that is perfectly fine because the channels here are formed by this gate to source of the NMOS. The channels of the PMOS are formed by gate to source of the PMOS. Right, so what we are interested in is whether that there is a channel path for this capacitor to charge or discharge. Right, in this case it is charging because the power supply is VDD. So I have switched on the power supply. Right, so now for the NMOS, the VGS value, right, so this is the VGS value, so the capacitor, while it is charging, right, through this particular path, the capacitor is charging, so the voltage is going to increase. So increase in the source voltage for the NMOS is going to reduce this VGS value for the NMOS. So it can increase till it reaches VDD minus VT. Right, so as we know that the NMOS transistor is going to pass a degraded logic 1, whereas the PMOS is going to pass a logic 1 successfully, right? Because this VGS value is independent of the capacitor charging effect here, which is completely on the other terminal. So the VGS here for the PMOS is nothing but minus of VDD, right? So it will always have this path for charging. So now I have one path, so let me draw using a different pointer. So I have one particular path here and another path here. So I have two paths for charging the capacitor. So the charging rate will be higher. So it will take less time for the capacitor to charge when we compare this particular transmission gates, when we compare with that of the only single PMOS transistors, because the paths are now two. So it is also charging from this particular NMOS path. It is also charging from this PMOS path. So at the output side or this particular side, the capacitor charges and then reaches to VDD minus VT, after which the NMOS will be off. NMOS goes into the cutoff, right? After VDD minus VT, only PMOS transistor will be on. So the channel of the PMOS will be there to charge the output from VDD minus VT to VDD, right? So from 0 to VDD minus VT, NMOS will be on. So 0 to VDD minus VT, PMOS will be on. Beyond that, from VDD minus VT to VDD, only PMOS will be on, NMOS will be off. Okay, so the PMOS conducts, consists of a channel or has the channel path for charging the capacitor from 0 to VDD, whereas the NMOS conducts only from 0 to VDD minus VT, right? So the NMOS transistor and the PMOS transistor is going to charge the capacitor really fast from 0 to VDD minus VT, right? Beyond which VDD minus VT to VDD, only PMOS transistor is available, NMOS transistor will be cutoff. Right? However, the transmission gate now, because both the transistors are stacked in parallel, and both the channels are available for the capacitor to charge, it actually passes logic 1 successfully. So if you remember, NMOS transistor was passing the degraded logic, right? But the transmission gates makes use of the PMOS transistor, which is passing the successful logic 1, right? So let's have a look at the transmission gate for the logic 0 passing. So on this particular terminal, if I switch off the power supply, I'll get again a 0 voltage here. So this particular terminal is now connected to the ground, right? And let's say that the capacitor is completely charged to VDD, right? So for an NMOS here, whichever potential is higher, that will be considered as drain. So that's why I've written drain here and then the source here. So VGS will always be VDD. So the channel which has been formed doesn't have any effect for the NMOS transistors, right? So the capacitor sees a path here and then it discharges, right? Because this part is only dependent on this VGS value and not on the capacitor discharging profile, not on the capacitor voltage, which is continuously decreasing because of its discharging path. So at any point of this discharging, this particular path doesn't have any effect. So the path is always there for the discharging of the capacitor, right? On the NMOS side. On the PMOS side, whichever one potential is higher on the PMOS side, whichever potential is higher on these two terminals, that will be called as the source terminal. So initially it is the VDD, so it will be called as S. The other one which is connected to the ground is called as the drain, right? And the VGS value now, as the capacitor discharges, there will be a path initially, right? Till the capacitor voltage decreases to VT, till that time there will be a path. Beyond that, the PMOS will not have a path because the VGS value now will be less negative than that of minus 0.3. So what we have is exactly a symmetrically opposite situation as that of for the logic 1, which we had seen earlier. The NMOS is available, the NMOS path is available from VDD to ground to 0 volts. So from logic 1 to logic 0, the NMOS path is available, whereas PMOS is available initially, right, from VDD to VT. Beyond VT, PMOS is off. So similarly to the last one, where there will be a discharging path, both the paths are available, the PMOS and NMOS, and thereby the discharging rate will be higher. The time taken for the capacitor to discharge, right, from VDD to VT will be really faster because both the transistors are on, VDD to VT. Beyond VT, only NMOS transistor is off, only NMOS transistor is on. So beyond VT, only NMOS transistor will be, the path made by the NMOS transistor will be made available. The PMOS will be off, right? So the NMOS conducts from VDD to 0, whereas the PMOS conducts only from VDD to VT.